Now let's try thinking about a different situation. We're going to instead of inserting a metal slab, same capacitor, same charge on the capacitor plates, but now it's a plastic slab. So it's an insulator. It has the same dimensions. It's 1 millimeter thick. It's right in the middle between these two capacitors. And ultimately, we want to eventually figure out what the potential difference is from A to B again. Before we talk about it too much, let me skip this for just a second. Originally, we had a delta V without the slab in there of negative 1,000 volts, and then we insert the plastic slab. Just use your intuition. Take a guess. Talk it over. See what you think. What's the new potential difference going to be? We saw for when we put the metal slab in there, it went down to negative 500 volts. Is it going to be the same? Is it going to be different? How much different? Okay, so everybody's sort of gut feeling is a good one. We would think that if the metal slab made the potential difference go down to negative 500 volts, we would expect the plastic slab to give us a potential difference of somewhere between negative 500 and negative 1,000, right? It's going to reduce it, but not as much. Why not? Why does this seem to make sense? Okay, the electric field inside, for one thing, isn't necessarily going to be zero, right? Because a plastic slab doesn't have mobile electrons, right? So how would I draw this? What's going on inside here? What do I need to draw? Yeah, polarized atoms, right? Induced dipoles, something like that. And like you guys said, there's no mobile electron seed, so there's no guarantee that E net is going to be equal to 0. But something happens to E net in here. And at any particular point, well, it might be hard to say what E net is doing because you've got all these polarized molecules in here, and depending on where exactly your observation location is, you could have, the net electric field pointing one way at one location or a completely different way at another location, depending on where you are. So it's a little bit messy, and it's hard to figure out. But we can use potential difference to reason it out in terms of what happens to the average electric field. If we were to kind of smear it all over and just look at an average, what's going on with the average electric field inside? And here's how it works. Let's just look at this polarized slab. If I were to kind of just isolate the polarized slab and think of, okay, we got all these induced dipoles. The applied field is making positively charged dipoles on the right, negatively charged dipoles on the left. So if I were looking at the electric field, and I just want to say the electric field due to these dipoles alone, at a location here, those dipoles would make an electric field pointing in what direction? To the right. Okay. So this is E due to the dipoles, right? And over here, the electric field due to the dipoles will be pointing that way, to the left? To the right, yeah, because the negative sides are closer over here, right? So just think about what would happen with one dipole, right? If you had one dipole, you've seen this. E points that way. E points that way, and then how does E point down here? To the left. So I can just sort of do that en masse, and I can see that this is going to be the pattern of electric field just due to those dipoles. We still have the electric field due to the capacitor, but I'm just looking at the field due to the dipoles. I'm going to choose a path to calculate a potential difference. It's going to start over on the right. It's going to go underneath underneath the plastic slab, underneath all the dipoles, over to the left, and then straight through back to where I started from. Okay. If I go round trip, if I go delta V round trip, and my path ends up where it starts, what should I get for delta V? Should get 0. Okay, and this is an important property to know. Okay, it comes from the idea of path independence, where we said the path doesn't matter going from A to B. So if you go from A to B along any path, you get some potential difference. Go back from B to A, you get the same same magnitude but opposite sign of potential difference. Round trip potential difference is going to give you 0. Okay. Well, let's look at the signs of the potential difference along some parts of these paths. And let me do this with a little program here. Let me get some dipoles. So in this program, you can just kind of drag a positive charge here and a negative charge here, and then click and show the electric fields due to these charges, etc. And let me do an example I already have written up. Let's get sources and get the dipoles. So there's a bunch of dipoles. Okay, the negatives are blue and the positives are red. Okay, so let's calculate the electric field at some places. There. Hey, what's going on? There we go. That's better. Okay, so it's doing the typical dipole pattern, right? Pointing away, pointing towards, curling around. Let me think about the potential difference. If I start here and go to here in the direction of the electric field, the potential difference along that part should be what? Positive or negative? Should be negative. Okay, so all right, I have to do it all in one sweep, so let's talk about it as we go along. I start here, I go around this semicircle over to here. Okay, so here's my starting point, that's my ending point. What sign of potential difference would you get? You start off with a path that's pointing downward, right? And it's kind of perpendicular to that electric field, so that should give you about 0. But notice as you're moving along this path, how does the electric field point? It's always going to have a component that is more or less in the direction of your path, right? Can everybody see that? Like, you can especially see it right here. I mean, I'm going basically in that direction. And here as well, I'm kind of going up. Then it starts to get more and more perpendicular, so it doesn't quite contribute as much. But overall, if I add the whole thing up, I should get negative, right? And then I go from here to here. That should give me what? Negative, because I'm going again in the direction of the electric field. If the round trip potential difference gives me 0, what should I get when I go through the interior? Should get a positive. Let's try it out. So I start here. Okay, it's giving me negative, I don't know if you can read it, negative 12.0 volts. And the blue indicates a negative potential difference. Red indicates a positive. Looks pretty blue. And my path is kind of shaky, but that's okay. Looks pretty blue. And it's all blue so far. And then it starts to get messy. Then it kind of goes a little bit blue, but then it gets really red again. And things are just going crazy. And then we go back. Okay, so it doesn't quite go to 0. It says negative 0.2. But that's due to round-off error in the calculation. But you can see the colors in here, right? I mean, there's a lot of red fuzziness indicating a pretty large positive potential difference inside, okay? You saw how the field was kind of going nuts in terms of the direction. But overall, you're getting a positive potential difference just due to that the field of the dipoles, just due to the field of the dipoles inside. So that says, what's that tell us? If we're going in the direction of the field of those dipoles. So here's the dipoles. If I went in that direction, if that was my delta L, and I got a positive overall, then the average electric field just due to the dipoles has got to be pointing in what direction? It's got to be pointing to the left. Okay, so that's the electric field due to the dipoles. All right, so that's the basic argument. We use this potential difference to determine how this field must point, but it's still inside the capacitor. So here's our capacitor again. This was negative and this was positive, we still have an electric field due to the capacitor pointing in that direction. But is E of the dipoles equal to E of the capacitor? You think that's going to be true? Probably not, right? In a metal it was. In a metal you have sort of the perfect amount of polarization to cause this electric field to cancel out. The dipole electric field isn't large enough to cancel the field of the capacitor out, but it does reduce it. And so the net electric field we get is something smaller, but still pointing in the same direction. So if I draw the plastic now, I have E net inside, which is smaller. I have E in the air gaps, which should be approximately what? Did the field in the air gaps change much? Did it change much for the case of the metal? No, so it's probably not going to change much for the case of the plastic, right? Because there's even less polarization going on. So we have the original E of the capacitor here. We have the original E of the capacitor here. And we have a reduced E net inside, or average E net inside. There's actually a relationship, experimental relationship, or empirical relationship, that tells us how much that E net is. And that E net inside is equal to the electric field, and I'll call it the applied electric field, which is the field due to the capacitor in this case, divided by a constant K. This capital K is called the dielectric constant. And it's a property of a material. Okay, so it's a material property. And for most ordinary materials, sort of well-behaved materials, there are lots of exceptions to this, but K is typically greater than or equal to 1. Okay? So if I have a number greater than 1, I'm dividing by a number greater than 1, my electric field has gone down. It's less than the original applied field. Okay? Examples of this value. I think I have some examples here. K for air. Well, K for a vacuum, by definition, has got to be just 1 because the field isn't affected by anything. K for air just slightly affects this applied electric field. It's 1.00054, something like that. For a typical plastic, it's somewhere between 2 and 3, okay, approximately. Paper, it's something like 3.5. Glass, it's approximately 5. So these are just giving you the values of how much the field is affected. Okay, a bigger dielectric constant means more polarization inside, meaning a greater reduction in that overall electric field. Okay, so this is kind of a long chain of reasoning. We used a lot of stuff here, but we've worked out that the potential difference should be reduced, not as much, but if we knew not as much as a conductor, but if we know that dielectric constant, we should be able to calculate it. So let's see if we can do that. Let's say, same situation. Let's say the dielectric constant of the plastic is 2. What's going to be the new potential difference from A to B? Think about what the value of the electric field is in each of those different regions, okay, just like we did with the conductor. Okay, so we have most of us saying negative 750 volts. Those of you said negative 250, you've got to be careful. We're talking about, again, the potential difference from A to B. So again, we're going through 3 different regions, right? One where we have the original electric field of the capacitor. So let's write it out again. We have E1x delta x1 minus E2x delta x2 minus E3x delta x3. So E1 is still 5 times 10 to the 5th. First distance is still 0.5 times 10 to the minus 3. E2, the new electric field inside the plastic is what? (2.5 times 10 to the 5th, right? It's going to be the applied electric field due to the capacitor divided by the dielectric constant, which is 2. Okay, 2.5 times 10 to the 5th times 1 millimeter times 1 times 10 to the minus 3. Continue it down here. Minus 5 times 10 to the 5th times 0.5 times 10 to the minus 3. Okay? So add that all together. We have 2 times this, so it's like 5 times 10 to the 5 times 10 to the 5th times 1 millimeter, essentially, when you add this term and this term together. So that gives you negative 500 volts minus another 250 volts. So that gives you negative 750 volts. So our intuition works out from before, right? We expected the potential differences to be somewhere in between 1,000 or negative 1,000 and negative 500, and it works out. Okay. So yes, question. I said that this electric field is the net electric field inside the plastic, right? The dielectric relationship says that the net electric field inside your plastic is going to be the applied electric field, meaning the field that causes the polarization in the first place. In this case, that's the field due to the capacitor. Okay? So in this case, it's 5 times 10 to the 5th, the same electric field that we had before, okay, divided by the dielectric constant, which is 2. So the overall net electric field turns out to be 2.5 times 10 to the 5th. Okay? Okay? Other questions here? All right, so you have a question on a dielectric for homework. The point of all this is, and we'll come back to capacitors later in the semester, but dielectrics actually have very important technological purposes. Pretty much every capacitor that's used in a real-life situation has a dielectric in between the plates, okay, or in between the conducting plates. And this is kind of a contrived example. Typically, the dielectric fills up the entire gap. What's it for? Well, for one thing, you need to physically separate the two charged plates. You can't have them in contact with each other, or the charge will bleed off. Okay, and the other idea is that because of the polarization of the dielectric, the net electric field is reduced from what it would be if there was just a vacuum in there. The more you reduce that net electric field, the more you reduce that potential difference across the two plates, and then you can essentially, given the same potential difference, charge up the plates more. You can add more charge to the plates if you put a dielectric in between them, and that's useful because we want dielectrics to hold lots of charge on either side in order to get that energy back again if we want to then use it in a circuit or some other application. Okay, so we'll come back to this later in the semester, but it's important because it's actually used a lot in real life applications. Okay.